Okie dokie, friends. So, on today's show, we take a look at the end points of the interval of convergence. Because we have been talking about, okay, I got a ratio test. Ratio test gives me an interval of convergence. If we're within the interval, then the series converges. If we're outside the interval, then the series diverges. But the ratio test fails at the endpoints of our interval. So what happens at the endpoints of our interval? And we talked a little bit about the nth term test, and we talked a little bit about telescoping series and things like that. But I want to give us one of the big ones today, and I want to give us one of the big ones tomorrow. So that's the way to start our week out right. Today, I'm going to give us the integral test. And the integral test sounds like this. Let the sequence a sub n be a sequence of positive terms. We won't allow negative terms until midweek. Suppose that a sub n is really a function of n where f is positive, continuous, and decreasing, that's the key, decreasing, for all x, and f is a positive, continuous, and decreasing function, for all n greater than or equal to capital N, where n is a positive integer. That is to say, if you were to plot the graph 1, comma A1, 2, comma A2, 3, comma A3, and so on, if you were to plot the points, eventually, after some point, that's your point, after some point, the function you get is positive, continuous, and decreasing. Then, the series, sum of the a sub n's, from capital N to infinity, and the integral from capital N to infinity of f of x dx, both converge or both diverge. Whatever the one does, the other does. This makes the first very strong connection for us between a series and an integral. Well, what was an integral in the first place? An integral was a sum of a bunch of rectangles. What's a series? A series is a sum of a bunch of numbers. So it makes sense that if we're going to talk about series, we're probably going to end up at some point talking about integrals. And if we're going to talk about integrals, at some point we're probably going to talk about series. It's not that big a jump to make. If the integral converges, then the series converges. If the series converges, then the integral converges. Two quickie examples of that. Does the sum of the 1 over n squareds converge? And of course, we know from previous lessons that the answer is yes. We're not quite sure why. So I will ask us to consider the integral from 1 to infinity of 1 over x squared dx. Notice, on the interval from 1 to infinity, 1 over x squared is continuous, it is positive, it is decreasing, and so the integral test applies. So what is that integral? Well, I take some antiderivative, sub, and subtract. As x gets larger and larger without bound, the thing inside those brackets is 0, minus, at 1, I get negative 1. That's 1. I get an answer. It is finite, It's not infinity, since the integral converges, the series converges. I will point out here, it's a pretty big deal. 1 is the value of the integral. It is not the value of the sum. The series converges to pi squared over 6. There is no connection between the number you get here and the number that this is. There is no connection whatsoever. Don't look for one. By the fundamental law of classroom examples, this one must blow up. And of course, you can quickly see with the integral test why this is so. We're going to make a comparison. No, we're not going to make a comparison. We're going to make a consideration. We're going to consider the integral from 1 to infinity of 1 over x dx. This is the integral of a continuous, positive, decreasing function. The integral from 1 to infinity of 1 over x dx is ln x evaluated between 1 and infinity. And we all know in a rigorous calculus class, we don't really write infinity up there. We write b, and we take a limit as b approaches infinity. We know that, but it's just us on YouTube. And so we're gonna get a little bit slack briefly. As b gets larger and larger without bound, ln of b approaches infinity. Ln of 1 is 0, and that diverges. Since the integral from 1 to infinity of 1 over x dx diverges, the sum of the 1 over n's from 1 to infinity also diverges. Whatever the one does, the other does. If you're trying to figure out whether or not a series converges or diverges, and the function associated with it is easily integrable, try it. It's not a bad idea. Now, again, I'll flip back and forth between slides here. 1 over n squared gets smaller and smaller, closer to 0 as n gets bigger and bigger. We're adding up infinitely many things that are pretty much 0, and yet that converges. Here, we're adding up infinitely many things that basically become 0, and yet that diverges, which does not appear to make any kind of logical sense, and yet it does. Incidentally, let's just talk about this one that we're looking at for a moment. It diverges very, very slowly. If you were to take the sum of the first 200 million terms, that sum is approximately 20. I'll try that one more time. If you were to add up the first 200 million terms of this series, your total would be about 20. And yet, when you add up all the terms, it blows up. Yikes. Let me generalize this for us. Let me talk about p-series. P-series are called p-series because they look like that. They're the sum as n goes from 1 to infinity of 1 over n to the p. The p-series converges if p is greater than 1 and diverges if p is less than or equal to 1. The p-series converges if p is greater than 1 and diverges if p is less than or equal to 1. So not only is this series a divergent series, it is the slowest growing divergent p-series. We can prove this. It uses the integral test. I'm not going to prove it with the integral test, but you can prove it with the integral test. You just represent this as n to the minus p, take an antiderivative, sub, and subtract, and you're ready. So time to play everybody's favorite game. Does it converge? Does it converge? And we've got 3 contestants on our show. We've got 3 over radical n. We've got the sum of 5 over n squared radical n. And we've got the sum of 1 over n ln n. So, how do I want to do this? I want to send you home to think about it. This is a p-series. So take a look at the definition of p-series. Tell me whether that thing converges or diverges. This is also a p-series. I mean, you could just suck the 5 right out of there. Turn that denominator into n to the p and tell me if that thing converges or diverges. And then this thing is, oh, I wish I could expand, but I can't. This thing is not a p-series, but we have discussed in this video how to do that. So if it helps you at all, 2 of these don't converge. I will leave you to figure out which 2. All right, that's all I have. That's all I have, honest. I'll see you in class tomorrow. We've got to practice.